Okay, well now we have Ed who's going to tell us about, well, you can read the title, but Monte Carlo methods for spatiotemporal data.
Okay, and phylodynamic inference too. Two for the first one. Okay, I'd like to thank the organisers. Great to be back in Cambridge. So I'll just mention the collaborators on this: Carlos Bretto, my postdoc, Aaron King, an ecologist, and Junha Park and Alex Smith, two PhD students. So here's kind of a motivational data analysis. Well, this is actually simulated data, but the kind of thing we're interested in is fairly complex systems. So the complexity of the model, I think, scaling with complexity of the model is as important as scaling with the size of the data. So here we have, say, 100 sequences, genetic sequences, each of length 1,000. So we only have 100,000 data points, which by the scales of this workshop, I wasn't sure I could call it big data, so I've called it not small data. But I want to kind of emphasize the sort of complexity of the kind of models we're trying to deal with. So maybe we have HIV sequences from 100 infected individuals, but we're interested in the dynamics going on in the whole population that gave rise to those sequences. So it's kind of small. I don't know how well you can see what's going on here, but we can imagine a model, dynamic model, and we can imagine simulating from it, and we can imagine that our model might have diagnosed and undiagnosed individuals, and they might be in an early, middle, or late stage of HIV infection. And the sorts of things the scientists are interested in is how much of the transmission happens early on in the infection, before diagnosis, and during kind of the initial onset of the infection. That's important for epidemiology. And then they have all this genetic sequence data, and they want to put everything together in a model, and ultimately it boils down to you have a complex model, but there's a parameter you're interested in estimating. Okay, so to attack these kinds of things, what I'm going to tell you about today has a very kind of classical flavor to it, because even though you're dealing with these complex models, it turns out that some of the things we had to do to make progress on this kind of took us back to profile likelihood, issues of Fisher information, local asymptotic normality, smooth likelihood, Monte Carlo likelihood, and now so then we're going to take a quick tour through some of these things, which I guess are very well known to many of us, but I think many of which don't quite make it into the usual kind of PhD curriculum. So you never know whether the younger members of the audience who are doing all these exciting things still know their kind of bread and butter parametric statistics. But we're going to see that I think once we've gone through these kind of basic things, there's going to be something new and exciting, at least to me, so I want to tell you about it. Okay, so profile likelihood, well, we need to just set up some notation for the log likelihood lambda, and the maximum likelihood estimator, which is going to be theta hat. I'm going to put a theta hat star for the estimate, and then we're going to suppose there's a focal parameter which we're always going to call phi, and so theta can be written as phi and then some other psi, and then the profile log likelihood maximizes out over psi, and then it's maximized at some marginal maximum likelihood estimate. And then you can look at this profile likelihood function, take a cutoff delta, and that's going to give you some sort of profile likelihood confidence interval. I find profile likelihood a very useful applied tool, so I'm always kind of in some ways frustrated that it doesn't get into the PhD curriculum, so students have to be taught it each time. But I think there's some historical reason why that's the case. So profile likelihood confidence intervals are equivalent to likelihood ratio tests. That has a long history. In terms of the actual use of profile likelihood, the first case I know is Box and Cox's 1964 paper, where they did the chi-squared cutoff that we now think of as associated with profile likelihood. They call it maximized likelihood. In 1970, Cox and Snell called it profile likelihood. Back through the 70s, people were still calling it maximized likelihood. Then actually, Cox did the same thing again and called it partial likelihood. So he introduced 3 different names for this thing. Much of the work in the 1980s was on how to do something better than profile likelihood to get better asymptotic behavior. And then I think there was a bit of a resurgence in profile likelihood in semi-parametric inference in the early 21st century. Okay, here's some more super classical stuff, just defining the Fisher information, the observed Fisher information. So Fisher information is matrix I, observed Fisher information, I'll put a star there, that's kind of denoting the additional data dependence. And then we can get standard errors and confidence intervals in the usual way. And if we look at the profile likelihood and we take the second derivative of the profile likelihood, that should match what we would get if we just took the marginal component of the observed Fisher information. And because everything should match up, if the likelihood function is quadratic, then the profile likelihood should match the standard Fisher information confidence intervals. Okay, so there's a kind of a long-running question of, I guess, practical interest, whether you should do observed Fisher information versus expected Fisher information and how profile likelihood fits in with that. And I think people noticed a long time ago that sometimes it's just not sensible to use the expected Fisher information. And Efron and Hinckley kind of wrote eloquently in favor of the observed Fisher information, but they only really they only had formal reasoning based on special cases, and they had to kind of argue about ancillarity. It seemed very hard to make that into a general argument. And Lindsay and Lee Bruce Lindsay and Bing Lee in 1997 had, I think, a much more general result that's not nearly as well known, which is that if you go to a risk framework and you consider the problem of optimal mean square estimation of the squared error, so I guess there's a 4th power in there, then actually the observed Fisher information is in some sense second order optimal, whereas the expected Fisher information, the bootstrap, is not. Okay, so there's some sort of link between using observed Fisher information and using profile likelihood, because if there's any transformation that makes the profile likelihood, the log profile likelihood quadratic, then everything matches the observed Fisher information. And because of that, you might, in some sense, you might expect profile likelihood to work better than observed Fisher information, because you don't have to know H. As long as there is such an H that makes things quadratic, then the profile does the right thing. Okay, so when you start thinking about how to prove things related to quadratic log likelihoods, then Lucien Lecam's theory of local asymptotic normality is never far away. So I guess many of you will be familiar with local asymptotic normality. The basic assertion is that the log likelihood is in some sense asymptotically quadratic, and this has been useful in the framework of semi-parametrics. And I guess the details of local asymptotic normality is all to do with the exact with the exact form of this quadratic limit that turns out to have nice consequences for inference. So now let's turn to inference. There's the Lecam's one-step estimator, which is a famous estimator in this context, where you basically take the log likelihood on a finite number of grid points, fit a quadratic, and obtain the maximum of the quadratic. We're going to call this one-step estimator the maximum quadratic likelihood estimator for reasons that should become apparent. So MQLE is efficient under local asymptotic normality, and if everything's super regular, local asymptotic normality is essentially equivalent to asymptotic normality of the MLE, but local asymptotic normality is weaker, it's easier to show, and also the MQLE can succeed when local asymptotic normality holds, but the MLE behaves badly. I guess theoretically people like local asymptotic normality because it can be easier to prove things about. One sort of practical issue is who would use local asymptotic normality for data analysis, meaning the MQLE estimator, if the log likelihood is grossly non-quadratic. And so here's kind of one approach to deal with that. Here's just an example of a non-smooth likelihood where it doesn't satisfy the Cramair conditions. You can still compute the MLE, but the maximum quadratic likelihood estimate is 15% more efficient. But there's also something called an MSLE, a maximum smooth likelihood estimator, where you just replace the quadratic by your favorite smoother, and that also does better. It basically matches the MQLE. And so there's two perspectives. Like from a purely theoretical perspective, it's nice to know you can do better. From a practical perspective, it's actually useful to notice that you don't do worse, because this thing can actually be easier to work with, particularly when you have to rely on Monte Carlo approximation of the likelihood. So this is the first indication of how we're going to head back to these complex inference problems. Okay, so how do you do maximum smooth likelihood estimation? It's very similar to the MQLE. You evaluate the log likelihood on a grid, but now you fit a smooth curve through these points, and as long as the smoother fits a quadratic through points that are close to a quadratic, you recover all the asymptotics of the MQLE, while having something that kind of is, I think, more natural and sometimes performs better in finite sample properties. If you want a smoother that does this, the lowest smoother in R, which is many people's go-to smoother anyway, has this property because it's a local second-order polynomial smoother. Okay. Now we're going to start heading back to dynamic systems and Monte Carlo methods. So when we have these kinds of complex stochastic dynamic systems, we're pretty much limited to Monte Carlo methods if we want to access them. And in principle, we can evaluate and maximize the likelihood function, and then we can construct confidence intervals, hypothesis tests, and do all the kind of scientific stuff we want to do. The focus of this talk is what to do when we can't make the Monte Carlo error small. So if we can just keep grinding away with the computer until the Monte Carlo error is small, then we have our likelihood framework, we're in business. If we, as data sets become larger and more complex, no reasonable amount of computation can render Monte Carlo error negligible. That's basically saying in the Monte Carlo kind of framework, we can't expect convergence. But we still want to do profile likelihood methodology, and we want to make allowance for this fact that things will not have converged. And we're particularly going to do this in the context of dynamic latent variable models, which the HIV example I put up at the start is one of those. Okay, so how do we go about linking Monte Carlo methods with these kind of theories of maximum smooth likelihood estimation? We basically need a metamodel for Monte Carlo. And what's a metamodel? A metamodel is just a statistical model fitted to the output of a Monte Carlo algorithm. And this equation M1 really just says we're going to model these little check marks represent Monte Carlo quantities. So the Monte Carlo profile is going to be the actual profile plus some bias plus some noise. This noise is going to be independent by construction because we're using separate Monte Carlo seeds at different profile points. And this bias is really the critical thing, but assuming we have a substantial amount of information in our data, so we're localized in parameter space, it's pretty reasonable to imagine that the bias should be constant and the variance should be constant near the in a neighborhood of the maximum. Okay, so we complete the metamodel by proposing parametric or non-parametric specifications for the profile likelihood. And the simplest thing in the context of local asymptotic normality is to make a quadratic metamodel, and then we're really back to a regression situation for the profile likelihood. So let's see, we have these unknown coefficients which are the true likelihood in the metamodel, and we have a regression problem, and that regression problem lets us split the resulting error into two parts. We have a statistical error, which is from the uncertainty in the data viewed as a draw from the statistical model, and that's the thing we're most familiar with. And then we have Monte Carlo error, which is the error resulting from the incomplete Monte Carlo convergence. And because we're in a regression setting, we can now just go ahead and analyze these things. And we can do a delta method, and we get a Monte Carlo standard error on the maximum. And we know about the statistical error because that comes from the usual asymptotic statistic theory. And then we can combine these things and we have a total error. And now we can convert this total standard error to a cutoff on a Monte Carlo adjusted profile. And this really is no different from the usual duality between the usual standard errors and the usual profile cutoff. They're both defined in a kind of asymptotic quadratic justification, but using the profile kind of gives you a little bit of extra leverage when you're not quite in the asymptopia. Anyway, we can go ahead and produce this cutoff, and our Taylor series expansion, the previous slide, gives us this formula for a profile cutoff when we have the non-trivial Monte Carlo error. And just as a sanity check, if the Monte Carlo error is 0 and you want a 95% confidence interval, you better get the most famous 1.92 profile cutoff back. Okay, and so this is basically what we're going to do. Okay, and we call this procedure a Monte Carlo adjusted profile. Here's kind of a toy example where we're just trying to do something really simple, which is a log normal model, but we're going to basically make the importance sampling hard so that we can pretend that it's a hard problem and we can't really hit the likelihood. And we can see here when we fit our smoother to the Monte Carlo profile points, we're not at the true profile, which is the dashed line, but that doesn't matter for the confidence intervals. We still get good confidence intervals with good coverage. And that's kind of the magic of the Monte Carlo adjusted profile. There's some bias which we don't know, we don't need to know, but it doesn't get in the way. And we can compare with other methods. There's maybe different ways you could do a bootstrap, but we did a bootstrap, and the quadratic method here is this MQLE, also applied to the Monte Carlo profile. And the MCAP does a little bit better, but it has other advantages. The MQLE has the usual problem that if things get too far from quadratic, it doesn't really make sense. The bootstrap has the problem that these are very computationally intensive things, and so the bootstrap is not necessarily that's a lot more computation. On a toy example, you can do it. Okay, so now I want to start kind of connecting this with the kind of dynamic models that we're interested in. So here are some statistical challenges for nonlinear mechanistic modeling in ecology and epidemiology. You have these dynamic models, you want to combine measurement noise and process noise, you want to include covariates, but you don't just want to, you don't want to be forced into some linear model, you want to include the covariates as the science recommends in mechanistically plausible ways. You want to deal with continuous time models despite the discrete time data. You want to have interactions in coupled systems, and you have latent unobserved variables. All these things we saw in the example I showed you on the first slide. You may also have to deal with spatiotemporal data, and more recently you may have to deal with genetic sequence data. Now the points numbered 1 through 6 were enumerated by Otto Bjornstad and Brian Grenfell in a kind of influential science paper, kind of raising a challenge. And 1 through 5 of these, basically, if you're into time series, you'll recognize these as a state space model, sometimes called a partially observed Markov process. And nowadays, these can be fairly routinely solved. So here we're focusing on 6 and 7. 7 has recently become increasingly important in epidemiology. The kind of problem was defined by another paper by Brian Grenfell and collaborators in 2004, and well, that's basically the example. Our approach to that is the example on the first slide that I'm going to come back to soon. Okay. Here's a little more on the problem of inferring population dynamics from genetic sequence data. So we think, in principle, that the genetic sequence data on members of the population should let us answer questions about what's happening in the population, things that we don't observe but ultimately give rise to the genetic footprint. And this challenge of extracting that information is called phylodynamics. And people have tried to do that in various ways by, say, estimating phylogenies and comparing the phylogenies with what they think is going on in the dynamics. and it was basically considered implausible to just go ahead and set up a Monte Carlo scheme, calculate the likelihood, and do likelihood-based inference. And so we put a lot of work into showing that you could just about do that, and we did that, and then we found that even when we tried our hardest, we still had this residual Monte Carlo error that wouldn't go away, and that's why we were kind of that's why we were working quite hard trying to find a methodology that worked in the presence of this residual Monte Carlo error. Okay, so I guess here's the same slide as a reminder. Let's see if there's anything more I want to say about that now. No, I think I'm gonna go on. I'm not going to show you the actual model, but you can probably imagine that it maybe has, say, 10 or 20 parameters explaining how different people meet and infect each other and go through different stages of illness. And then there's a whole lot of stochastic randomness that you could almost kind of think of as dynamic random effects that essentially you have to integrate out over to get the likelihood. And so if you work hard on your Monte Carlo scheme and then spend 10 days on 500 cores, you might get a profile likelihood that looks like this for HIV transmitted by recently infected diagnosed individuals, and that's really the question that you're trying to answer. And you carry out this MCAP methodology, and you find that if you want to allow for the Monte Carlo noise, you have to use a cutoff of 2.35 compared with 1.92. And actually, that's not a big price for all this Monte Carlo noise. If you were on a tighter budget, you probably could have spent less time on your computer and got an acceptable level of error quicker and cheaper. But okay, so the standard error of the profile evaluations is about 25 log units. So that's basically much bigger than the kind of inferential scale of 1 log unit. Okay, I promised to talk a bit about partially observed spatiotemporal systems too, and I guess the main general point here is that this is another thing of interest that challenges currently available methodology. So the basic method for dealing with low-dimensional partially observed nonlinear Markov processes is sequential Monte Carlo, abbreviated to SMC, but this scales poorly to high dimensions, and Bengtsson, Bickel et al. Kind of actually did the math to show that. But more, and that made it look like, okay, sequential Monte Carlo is right out in high dimensions. But then Rebeschini and Van Handel came along and said if things are weakly coupled, then there is at least hope. They proved that there exists a sequential Monte Carlo scheme that doesn't have this exponentially bad scaling as long as things are weakly coupled spatially. But the algorithm of Rebeschini and Van Handel is not very practical. I don't think anybody's actually used it successfully on any example, but it kind of holds out the promise that probably there do exist practical sequential Monte Carlo schemes that scale to these larger data sets. And my PhD student, Junha Park, developed some such algorithm which scales maybe not to the huge kind of atmospheric science data sets, but certainly to city-level epidemiological data sets. And so I guess I'll just show you the kind of data he was fitting to. Maybe you have 20 cities, and within each city you have some dynamics of susceptible latent infectious recovered individuals, and then you also you're interested in doing a space-time analysis, so you're interested in how movement between cities might be critical for the dynamics. And you can see here that smaller cities have fade-outs, and then you need a reintroduction. In London, you pretty much have measles all the year round, pre-vaccination, and then in some of the middle cities, there's some other kind of dynamics. So how a disease persists in a population is important. Maybe sometime soon we're going to try to eradicate measles from the world, and so people want to know how it persists, and it persists as a spatiotemporal process. Okay, so here's just one example of the MCAP, because from the point of view of the MCAP, the relevant thing really is just that you have some complex system and you can get some super noisy Monte Carlo estimate of the likelihood, and that doesn't stop you doing effective inference. This is really a kind of provisional result. We could have hit this with more Monte Carlo effort, but I was just kind of I guess it's useful to have these tools not just for your final results, but also as you're moving through the model development. Okay, and this is again a validation study. This is a simulation study, the MCAP. Although we never know what this vertical shift is here, we know the actual profile is somewhere up here, but the statistical properties of the Monte Carlo adjusted profile still seem to work. Okay, if you don't have the MCAP and these kind of Monte Carlo intensive methods, what do you do? Well, I mean, people interested in these problems, so they have tried to do some other things, and I should say a little bit about that. You can compare the data with simulations using some summary statistic. That's something you can always do, a kind of simulated method of moments, or approximate Bayesian computing, synthetic likelihood, nonlinear forecasting, different kind of frameworks for doing this kind of thing. The problem is that it's really hard for these complex nonlinear high-dimensional systems to find low-dimensional summary statistics that capture a good fraction of the information in the data. That's not necessarily something you can easily have a theorem about. It's more something that you pick up experience with in the literature, and so I have my favorite examples for this, but also from my experience I kind of believe it. Whenever I've tried these methods with matching summary statistics, they lose a lot of information in different directions. There's also the danger that you'll choose the summary statistic that agrees with your particular theory, whereas the likelihood, once you have the model and the data, it defines the likelihood function. It's kind of fairly objective from there. Comparison with Bayesian computation. I have a pretty heavy slide on this, which there's not that many Bayesians in the audience, and I can talk to them afterwards. But perhaps the main point I want to make is that there's not as far as I know, a Bayesian analog of this MCAP yet, and there are actually theories saying that the main Bayesian alternatives to the methodology I showed you, basically you need to get that Monte Carlo error down to about 1 log unit, and that's kind of optimal for convergence, and that's just not going to happen on these problems. So unless somebody comes up with some way around these theoretical difficulties, then you're kind of stuck with the frequentist inference. Another thing, so there's been a lot of Bayesian work in kind of hierarchical models and models with some sort of extra structure you can exploit. But one of the nice things about the MCAP is you don't need any structure, and so it applies in these rather general complex system situations. Okay, So I'm going to conclude about the MCAP, and then I want to tell you just a little bit about one of the algorithms that really lets us do all these kind of Monte Carlo profiles. So MCAP's simple and general approach to inference when the signal-to-noise ratio in the Monte Carlo profile log likelihood is sufficient to uncover its main features up to an unimportant vertical shift. That's basically what it does for you. And it can be effective even when you can't carry out other techniques like MCMC. The stage of development of the MCAT, we kind of developed the methodology kind of because we needed it, but I think there's more places it can go, and if we get around to, we'll slowly work out the theory, but there are probably some people in this room who could work out more of the theory quicker. Like I've shown you how to do confidence intervals, but because of this bias shift, if you want to do model selection, AIC or likelihood ratio tests, then you've got a different problem, and we don't know how to do that yet. Okay, so here's a change of shift. I thought I'd tell you just a brief introduction to the algorithms we use to construct the points on the profile likelihood to which we apply the MCAP. And our favorite algorithm right now is called IF2, iterative filtering 2. That kind of suggests there was probably an IF1 that I'm not going to tell you about, but I'm going to tell you about the IF2 algorithm briefly, and let's start with what it does in the terms of what comes in and what comes out. So the input is going to be some kind of dynamic model, and the key thing here is the format in which the dynamic model is input. You need a dynamic model. If it's a partially observed Markov process, it consists of a transition density and a measurement model. But we don't need to evaluate the transition density, we just need a simulator. And that turns out to be really convenient for complex models. If you have some large continuous time process, you can often write down a simulator, whereas the transition probabilities over discrete time you may not have access to. So methods that are based on a simulator for the transition density we call plug and play. You could call them simulation-based too, but simulation-based kind of suggests you're going to simulate whole trajectories over the whole length of the data, whereas we're going to be smart and kind of cut and paste carefully chosen sub-trajectories. So formally it's plug and play if you can simulate from any arbitrary time to any other arbitrary time. Then you need a measurement density, you need data, it's an iterative algorithm, you need to know how long to iterate. It's a Monte Carlo algorithm, so you need to know the Monte Carlo sample size. For sequential Monte Carlo, the sample size is called, each member of the Monte Carlo ensemble is called a particle. And then the parameters are going to be represented by some other set of particles. And in an iterative filtering algorithm, the parameters are going to be perturbed while you filter, and so you need to have a perturbation density and a perturbation scale. And you filter recursively through the data, and then you output the parameters you get, and you hope in theory and practice that will collect in the neighborhood of the maximum likelihood. And it turns out that sequential Monte Carlo also gives you an unbiased estimate of the likelihood. So that kind of fits in with the other part of these profile likelihood methods. Here's the pseudocode for the actual algorithm, which it's one of these things where it's relatively simple if you know what sequential Monte Carlo is. If you don't, it's probably more than I can do in a minute or two. So you have some iteration going around the outside. In the inside, you do sequential Monte Carlo with parameter perturbations, and that's really all it is. So by sequential Monte Carlo standards, it's a simple algorithm. And it turns out that each iteration approximates a Bayes map, and here is the Bayes map. Again, I think I don't really have time to explain it super much. If you want to prove the convergence, it's a little bit of a game because iterated Bayes maps are not contractions in the usual metrics. Nevertheless, I felt I should show you a couple of theorems about this thing. So this iterated Bayes map does converge to a something, and the sequential Monte Carlo approximation also converges uniformly to that something under suitable regularity conditions. This is basically a filter stability result, but because the perturbed Bayes map is not a contraction in the usual metrics, you have to move to the Hilbert projective metric to get the convergence, and then move back to whatever norm you want. Okay, so this map converges, and we then want to know that if the perturbations become small, it converges to a neighborhood of the MLE. And here's kind of an outline of that proof. It's basically you need to check that it can't converge anywhere else. So anywhere else it wants to converge has a likelihood penalty, and then as you do repeated iterations, the likelihood penalties build up, and so it really has no choice but to head back to a neighborhood of the MLE. And I think at this point I shall thank you for your attention.
Any questions? I had a quick question. So at some point you said that something along the lines of, the Monte Carlo profile likelihoods sort of should look like shifted versions of the real profile likelihood under appropriate conditions. So do we have any idea what that might look like?
Right. So yeah, there's a reason the theorems that I showed you were for the other part of the talk. I don't think we do. I mean, we have. So I guess if there is some bias and it's presumably a function of the profile parameter phi, right? So it's kind of clear that as you localize, that bias has to get locally small. But I don't think we know more than that.
Related question. Earlier in the talk you mentioned the quadratic or smooth likelihoods were more efficient. I was wondering if you could comment on finite sample sizes, what the bias variance trade-offs were there between the different approaches.
Right. So
you had a graph as well showing how the...
Yeah, I guess I have one specific... You're thinking of this kind of...
well, the slide I'm thinking of was earlier when I thought of the question, but... Yeah, that one.
This one. Right. So do I have any kind of... Right. So I guess that comes back also to issues of like how would you choose the smoothing parameter, right? In a finite sample, you have to choose the smoothing parameter somehow, right? And I mean, once you have a procedure, you can test it by Monte Carlo. So you can validate the procedure you have, but some sort of optimality, some kind of adaptive result on the how to choose that bandwidth parameter is something we don't have.
All right. If there are no further questions, let's thank Ed and head to lunch.